looked at solving systems of equations by graphing, but another great method is to use substitution. With the substitution method, we never visually see a graph. At the end, once we have the solution, we simply have the coordinate where these two lines would cross at. So it's really interesting that you can get that coordinate but never visually even see a graph. In order to use substitution, one of my variables has to be isolated. So you can choose either equation. I usually just choose what looks easiest. What I mean by isolate a variable, let's say we use equation 1, and I'm going to get x by itself. Why did I choose x? I don't know, because it looked easy. It didn't matter. I could have gotten y by itself. But look how easy it is to get x by itself right here. X equals y plus 5. Again, I could have used the second equation. I used the first. I could have gotten y by itself, but I got x. It's your choice, okay? Well, once I have x by itself, I can go to equation 2, and equation 2 says 2x plus y equals 1. Well, I know what x equals. Why did I have to even write x there? I can say, put parentheses where that x was at, and since I know what x is equal to y plus 5. Instead of saying 2x, I'm going to say 2 times y plus 5. And now I have an equation that has no x's in it. It has just one variable. It has all y's, and I can solve for y. First, I need to clear my parentheses. 2y plus 10 plus y equals 1. Therefore, 3y plus 10 equals 1, and I can subtract 10 from both sides and get that 3y equals negative 9, so y equals negative 3. Well, this is not my final answer. I probably shouldn't have put a box around it. In fact, I'm going to erase that really quickly, because my final answer will be a coordinate. And I just know that negative 3 is my y value. So if I have y, I found y using substitution, how in the world am I going to get x? That's just one of my variables. Well, I'm going to use substitution on x as well. So it doesn't matter which equation you use. I'm going to choose the first one. X minus y equals, let me go back and look, equals 5. Well, why did I have to put y there? I know what y equals. X minus negative 3 equals 5. See, I just used what I knew y to be. I just plugged that in, substituted it. Okay. Now I can see I have an equation now that only has one variable. It just has x, and I can solve for x. It no longer has two variables. So x plus 3 equals 5, and I can subtract 3 from both sides and get that x equals 2. So my final answer, wherever it went, there we go, is 2, negative 3. That is the coordinate at which those two lines would cross at. I have one more example of substitution that I want to show you. And remember, in substitution, you have to have a variable that's isolated. And what we mean by that, it has to say x equals by itself, or either y equals by itself. And we actually already have that in the second equation right there. These two equations didn't start off in the same form like they normally do, and in this case it made it easier. So I can just take that first equation and leave out the y. I can say x plus where the y would go equals 3. Okay, and y, okay, of course it went there originally, but y is equal to 4 minus x. So that's what I'm going to write down there. And now I have an equation that only has one variable. Well, there's two x's in there, but they're the same, and so I can solve for that one variable. And so we have x plus 4 minus x equals 3. And I go to simplify this and watch what happens. This is weird. Those x's cancel. You had a positive x and a negative x, and you get this statement right here. 4 equals 3. Does 4 equal 3? No, it does not. Therefore, the answer to this system would be no solution. You can't do anything else with this. It gave us, it produced a false statement.